All right, let's go ahead and get started. Who has questions? Neither of you. Okay, so let's take a look at what we're doing for this module. We're looking at two concepts that deal with bonding. We're looking at valence bond theory. That's one of the things. And I'm just going to call this VO theory. And in contrast to valence bond theory, we're going to look at another theory called molecular orbital theory. Which I'm going to call MO theory. Now, if you can see my screen, give me a thumbs up. If you can see what's going on here, like my finger, my hands. You can see this, Jackie? Or can you see this, Jackie?
My reaction buttons aren't working, but
Okay.
yeah, I can see it.
All righty. So we're going to be looking at these two theories in contrast to one another. And they deal with how bonding works in molecular compounds. So let's look at valence bond theory. In valence bond theory, you get a bond when two orbitals overlap. And these orbitals are atomic orbitals. That means that the orbital is on the atom itself. Now, the orbitals that we're used to from the past are s orbitals, which look like circles, p orbitals, which look like infinity signs, but they're three-dimensional. Right, so this would be the py, this would be the px, and this would be the pz, where they match the Cartesian coordinates. So that's what we're used to for atomic orbitals. And the deal is that when two orbitals overlap, you get a bond. So if you have a hydrogen with a 1s and a single electron, you could write that this way. And if you had another hydrogen that looked just like this, so I'll write that over here. These two hydrogens could come together, and these are the 1s orbitals overlapping, and here's your bond. Now, I draw those electrons in the overlap between the two orbitals, but they're actually somewhere in here. So this is a better description of what's going on here, is not to distinguish the overlap by a Venn diagram type of thing, but to draw something like that. So are we okay with this so far? Okay, great. Now, what happens when you have something else like hydrogen making a bond with, say, fluorine? Now, for fluorine, we've got 1s, 2s, and 2p. So this is what fluorine looks like. And we're going to make this guy here the 2px. So what happens here in this overlap is you've got this 2px with an electron in it. These are the same thing. This is an orbital diagram of it, and this is an actual picture of the orbital. So what can happen here is that you can have this orbital overlap like that, where this is a fluorine and this is a hydrogen, and here's your bond. And it's called a valence bond. And the reason we call it a valence bond is because you're using valence orbitals. A valence orbital is the same as a valence electron, It's an electron in the outermost occupied shell. So in hydrogen, the only shell that's occupied is the 1. In fluorine, the outermost occupied shell is the 2. So this is a valence orbital in the valence shell, and this is a valence orbital in the valence shell, and you have the bonding. Okay. So what would happen if you had CH4 and you wanted to try to explain bonding in CH4? Now, we already know that CH4 looks like this. We learned this from Vesper. Now, we gave no reason for an orbital reason for why this assumed the shape it did. We just said it assumes the shape it does because each pair repels the other pairs, and they tried to get as far away from one another as possible. That's the only justification we gave for the shape. However, if we look at bonding, valence bond theory here, we're going to find out that we need to make some adjustments. So here's carbon. And here's hydrogen. So you can see here that we only have two valence orbitals with an electron each that can bond. So presumably carbon can only make 2 bonds with 2 hydrogens. But someone said, you know what, maybe this is what happens. We're going to take one of these electrons and stick it in a 2p orbital, and that way we can get 4 bonds. And the reason this happens is because when this electron gets put over to here, it costs energy, but when it makes a bond, it releases energy, and the payout is favorable. So this is what happens. And so you have 4 of these hydrogens with a 1s. Now let's take a look at this in more detail and show you why it doesn't work. So these are the valence orbitals. And here's what that carbon looks like with its valence orbitals. First of all, this is the 2py with an electron in it. This is a 2px with an electron in it. And then we got this guy here, which is the 2pz with an electron in it. Remember the Cartesian coordinates. So those are 3 of the electrons. And the 4th electron, of course, is this guy right here, which we're going to put over here, which is in the 2s. So this is a 2px, this is a 2py, this is a 2pz, and this is a 2s. So those are the 4 electrons. So how would bonding look like in a case like this? Well, you can imagine that one of your hydrogens would bond like that. And so here, what we'll do is we'll put a carbon here and we'll put a hydrogen here straight up. One hydrogen would be over here. And you'll notice these are 90-degree angles. And another hydrogen would be here coming out of the plane. And again, this is a 90-degree angle. And where would we put the bond to this one? Well, we'd kind of do the Vesper thing and say, well, the bond to this one is going to be kind of back here somewhere, away from all these others. And so you get a really odd looking creature where you've got 90-degree bonds here. This is a 90-degree bond also. So you get these 90-degree bonds, and then you got this one hydrogen kind of sticking out the back. So if I drew it another way, it would look something like, well, I'm not going to draw it. And this is not tetrahedral. So someone came along with this idea. I said, well, what if we did this instead? Whoops, my bad. We're going to take these 4 orbitals and we're going to make 4 new orbitals. They're going to be made out of these 4 orbitals. So that means they're going to be 1 part s and 3 parts p. And when we make these new orbitals, we'll call them sp3, because we're basically going to take these 4 orbitals here, and we're going to take this much of one, this much of one, this much of one, this much of one, and make a new orbital called an sp3. So how many times can we do this? We can do this 4 times. So here's another sp3. Here's another sp3. And here's another sp3. So each of these orbitals is 1 part s and 3 parts p. And that's why they're called sp3. Okay, now these, since they're hybrid orbitals, meaning they're made out of more than one type of orbital, and since they're all of equal proportions s and p, they will have the same energy. Whereas over here, they're not all the same energy. So now we have 4 orbitals that are the same energy. So how will 4 orbitals that are the same energy arrange themselves around the center of an atom? And the answer is like this. Tetrahedral. Now, if we have 1, 2, 3, 4 electrons in these 4 orbitals, when they hybridize, how do we put the electrons in there? 1 per orbital. So here's how the hydrogens bond. And that's valence bond theory. So valence bond theory is basically that valence bonds or valence orbitals can hybridize and form new orbitals. So for valence bond theory, you have to be able to recognize hybridization. And it's real easy to recognize hybridization, really easy. All you have to do is count pairs. And these pairs that I'm talking about are the same pairs from Vesper. If you have 2 pair, you're sp hybridized. If you have 3 pair, you're sp2 hybridized. If you have 4 pair, you're sp3 hybridized, 5 pair, sp3d hybridized, and 6 pair, sp3d2. And if you look at the number of pairs, they equal the number of orbitals that you're hybridizing. We're hybridizing 2 orbitals, 1, 2. We're hybridizing 3 orbitals, 1, 2, 3. 4 orbitals, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. So recognizing hybridization is really, really easy. So let's take a look at a problem where we're trying to recognize hybridization. How many pairs here? If you think there's 1, give me an okay. If you think there's 2, give me an okay or a thumbs up. If you think there's 3, give me a thumbs up. If you think there's 4, give me a thumbs up. And the answer is 1, 2, 3, 3 pair. So let's go over pairs. A single bond is a pair. A double bond is a pair. A triple bond is a pair. Lone pair is a pair. A single electron is a pair. Those are all pairs. So if you had some atom with a single bond, that's a pair. With a lone pair, that's a pair. With a triple bond, that's a pair. With a double bond, that's a pair. With a single bond, that's a pair. How many pairs on this guy? If you think there's 1 pair, give me an okay. If you think there's 2 pair, give me an okay. 3 pair, 4 pair, 5 pair. Correct. 5 pair. So that's why this has 3 pair. So that means that this is sp2 hybridized. 1, 2, 3. 3 pair, 1, 2, 3. Okay, tell me the hybridization on this guy. If you think it's, well, tell me how many pair, first of all. If you think it's 1 pair, give me a thumbs up. 2, 3, 4. Correct. So if you think the hybridization is SP, give me a thumbs up. SP2, SP3, SP3D, SP3D2. Well, 4 pair means you have to have 4 orbitals. S, P, P, P. 1, 2, 3, 4. 1, 2, 3, 4. Now we don't write SPPPP. What do we write? SP3. So what's the hybridization on this guy? SP3. Okay, let's try another one. What about this guy? How many pairs? If you think there's 1, give me a thumbs up. 2, 3, 4. Good, 4 pairs. What's the hybridization? If you think it's SP, thumbs up. SP2, thumbs up. SP3, thumbs up. Okay, it is SP3. 1, 2, 3, 4. So basically, this would be a 1 right here if we put a 1 there, but we never do. What's 1 plus 3? 4. Okay, so that is implied as a 1, and that's how you get the hybridization. What about this guy? Give me a thumbs up if you think there's 1 pair, 2 pair, 3 pair, 4 pair, 5 pair. Okay, 5 pair. So what's the hybridization? If you think it's SP, give me a thumbs up. I'm going to write them down. So if you think it's the first one, thumbs up. Second one, third one, fourth one, fifth, fourth one. Okay. And that is correct because this is an SPPPD 1, 2, 3, 4, 5, 5. Okay. How many pairs? 1, 2, 3, 4, 5, 6. 6. 6 is correct. What's the hybridization? SP. SP2. SP3. SP3D. SP3D2. That's correct. So give me a thumbs up if you feel like you're kind of getting used to counting pairs and getting hybridization. Kind of getting used to it? So let me give you some weird ones. So how many pairs? When I point to the right one, you give me the thumbs up. 1, 2, 3, 4, 5, 6. I didn't see you vote, Harry, so we're going to try it again. You think there's 6 here? Okay, and the answer is 2. 1, 2.
Oh, do the little double bonds above the O not count? Above the oxygen?
I did circle the double bonds.
No, the I meant not the double bonds. Sorry, the bonds above the oxygens. Do those not count?
They do count. These are bonds and they count.
No, no, I meant sorry, not the bonds, the lone pairs above the oxygens. Do those not count in it?
Are these lone pairs on the carbon?
Oh, no, sorry,
So they don't count.
I got that mixed up.
Yeah, if they're not on the atom, they don't count.
Oh, okay.
Now
Yeah,
here,
so I got
how
that
many-
all mixed up.
how many pair on that oxygen?
Oh, and there'd be 3 on the
So
oxygen.
1 on the oxygen. 1. Give me a thumbs up when you get the answer. 2, 3, 4, 5, 6. You got to answer, Jackie. On this oxygen here, how many pair? 1, 2, 3. That's correct.
I was thinking of the whole thing for whatever reason.
Nope, it's just on that
Mixed
atom.
up.
So this is a good one to do. So what's the hybridization on this one? So remember, 2 pairs sp, sp3, sp, well, actually, I'm going to do this. sp, sp2, sp3, sp3d, and sp3d2. So on this oxygen, what's the hybridization? Give me a thumbs up when I get there. sp, sp2. Correct. Carbon, what's the hybridization? Give me a thumbs up when I get there. sp. Correct. How about this oxygen on the end? Give me a thumbs up when you get there. sp, sp2, sp3, sp2. Okay, sp2. So that's the hybridization. Let's look at bonding in this guy here. So we know the carbon is sp hybridized. So how will those 2 sp orbitals arrange themselves? Like this, linear. Now, that means that when you have the 2s and you have the 2p, these hybridize, these do not. So when they hybridize, what you get is this. You get a sp, an sp, and you still have 2 p's that are not hybridized. So what I've drawn here are the sps. Where are these guys? And the answer is, here's one of them. And here's the other one. They're still there. Have you got that? They're still there. Now, that's for the carbon. The oxygen, these 3 hybridize. What's the best way to draw these oxygens with 3 hybrid orbitals? And the answer is this way. Does that look trigonoplanar because it's supposed to? Another way you could draw the oxygen is this way. So this is the same thing as this, only it's laid down flat. So what I'm going to do is I'm going to draw those right here. Now, where is this guy? For this guy, it's right here. There's your P. Where is it for this guy? It's right here going in and out of the plane of the board. So I'm going to take one of these, this one in fact, and put it up here. And here's the P. And this here is a valence bond. Now I'm going to draw this other oxygen right here. And here's the other P. And this right here is a valence bond. So I've shown you how we get one of the valence bonds for CO2. But I don't show you how to get the second bond for each of these. So here's the second bond for each of these. It's easier to show it to you with these two. It turns out that this p orbital and this p orbital overlap, and this is a valence bond. So instead of a head-to-head overlap like this, you're doing a side-to-side overlap. Now you might say, well, there's way too much space between these for this to happen. It's impossible. You have to remember that this here is called a ball and stick model. Where the atoms are balls and the sticks are the bonds. But there's also something called the space filling model. And if you drew this using the space filling model, instead of having balls and sticks, you would have this. Where you don't show the bonds. The bonds are where the atoms touch. So when you think of the space filling model, you know absolutely for sure that these two p orbitals come close enough to touch and overlap. Okay? All right. Now here's another bond here. This p and this p. So this is a valence bond. So here, instead of a valence bond where you have two p orbitals that are straight up, you have two p orbitals that are side by side, horizontal, if you will. Okay. So this is these bonds here that are like this, that are not directly between the two atoms, are different than these bonds that are directly between the two atoms. These bonds with the head-to-head overlap, they're called sigma bonds. These bonds that are from two p orbitals overlapping side to side, they're called pi bonds. And the most difficult thing for people to understand about pi bonds is, you see this right here? That looks like two bonds, correct? Give me a thumbs up if that looks like two bonds there. You know it does, but it's not. It's one bond. So it looks like two bonds, but it's one bond. Pi bonds from side to side overlap. Overlap on the top and overlap on the bottom. Let's see if I can do that. So on the bottom and the top. So let me show you what the book does for a drawing that is supposed to be like this. Here's the book doing a similar drawing. So let me explain what's going on here. This is the molecule we're looking at, CH2 with a double bond right here. And each one of these has 3 pair, so it's sp2 hybridized, which means that the hybrid orbitals are going to look like these triangles here. And here, this is a sigma bond because it's a head-to-head overlap. Now, if we take this guy here and we tilt it like this, so that instead of being flat on the paper, it's kind of perpendicular to the paper, we have this drawing here. So if we tilt this, and I'm going to go ahead and draw in my book, I'm going to draw this tilted. So this is this part tilted, and we still have these p orbitals here. So what do these p orbitals do? They overlap. And this is a pi bond. And you see, this is the way I draw it with a, on paper, but look at what they do in the book. They say, oh, you know what? When they overlap, they form a ellipsoid, if you will, above and below the other bonds. Okay? So this is the way I draw it. This is the way your book draws it. If you're supposed to draw something like this on a test or homework, you can draw it this way. That's fine. And you can see the same thing down below for this molecule, where the oxygen is sp2 hybridized and the carbon is sp2 hybridized. The big difference between these two is simply that in this model, you have oxygens bonded. Well, in this model, you have oxygens or hydrogens bonded here, and here you don't. But they have the same type of hybridization. Okay, that's valence bond theory. So you need to understand how to pick out hybridization. You need to know how to draw them. And so what we're going to do now is we're going to look at drawing the different types of hybridization. So sp hybridization is simply this. Okay. So now with a drawing like this, the confusing part is that these are orbitals, but both sides of this one are one orbital. So p orbitals look like two orbitals, but they're one orbital. I'll say that again. A p orbital looks like two orbitals, but it's only one. So that's sp. sp2 is going to look like this. This is the best way to draw it so that you can see that the p orbital is perpendicular to the sp2 orbitals, but you can also draw it this way. And in this case, the p orbital is going in and out of the plane of the board, so you can see that it kind of overlaps this guy. And if I want to do a better job of this, what would I do? I do this. Where this is the p. There's sp3 hybridization, which looks like this. And this, by the way, is called linear. This one's trigonal planar. This one's tetrahedral. And then there's two more. sp3d is going to look like this. And then there's the last one. I'm going to pause for just a minute here. Okay, if you can see the paper, give me a thumbs up. Okay, and this is called trigonal planar, or excuse me, trigonal bipyramidal. So if this seems to be like flashbacks back to VSEPR, it certainly is. And sp3d2 is going to look like this. And we call that octahedral. And the angles are the same as VSEPR. The way this differs from VSEPR is it actually gives us a reason for why the orbitals are the way they are. They hybridize. Okay? The other thing that we're going to look at with this valence bond theory, and then we're going to go on to MO theory. When we take a look at something like this, let's take a look at all the different types of bonds here. We have a sigma bond here. We have a sigma bond here and a sigma bond here. A sigma bond here and a sigma bond here and a pi bond here. So we have a net of 5 sigma bonds and 1 pi bond. So you should be able to count bonds. Now let's take a look at this thing drawn this way. This is a little off, but you'll forgive me. So here, how do we know something is a pi bond? And it's really simple. Single bonds are sigma bonds. Double bonds are 1 sigma and 1 pi. Triple bonds are 1 sigma and 2 pi. That's the way it always is. Are you guys clear on that? So here, how many pi bonds? And the answer is 1. So if one of these is a pi bond, what's the other? The other is a sigma. So sigma, 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 5 sigmas. So I'm going to draw a structure and you're going to tell me how many sigma bonds and how many pi bonds. So you'll have to turn your mic on for just a minute. So let's see. So this is the complete drawing with all the electrons. I'm going to give you the easy one first. How many pi bonds?
2.
2 is correct. Do you agree, Jackie?
Yeah.
Okay. Now, Jackie, I'm going to let you have the first call. How many sigma bonds?
Yeah, I'm not really sure.
Well, pi bonds are 1 sigma and 1, or excuse me, double bonds are 1 pi, 1 sigma.
That's
Single
it.
bonds are always sigma. So how many single bonds here?
So there's 4 single bonds.
So that's 4 sigmas. How many pi bonds? Or how many double bonds?
There's 2 double bonds.
And each double bond is 1 sigma and 1 pi. So how many sigmas here?
So there's 2.
Okay, so how many sigmas total with the 4 and the 2?
Oh, there's actually 5 single bonds. So it would
Yeah,
be
there
7
are. You
total.
missed that one, didn't you?
Yeah.
So 1, 2, 3, 4, 5.
Yeah. So
1,
there'd be
2, 3, 4, 5, 6, 7. 7 sigmas. Capiche?
yeah.
Okay, let's take a look at another one. Okay. How many pi bonds here?
3.
What do you think, Jackie?
Is there also 3, I think?
3. 1, 2, 3. How many sigmas? 1, 2, 3, 4, 5, 6, 7, 8, 9. And that's all there is to counting sigma bonds and pi bonds. Is that clear?
Wait, isn't there 10 sigma?
Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9. Why do you say 10?
Well, there's 7 single bonds.
1, 2, 3, 4, 5, 6, 7, 8, 9.
But isn't the triple bond 2 sigma?
No, the
Oh,
triple bond is 2 pi's. That's how we
oh,
got 3 pi's. 1, 2, 3.
oh, but it's only one sigma.
Right.
Oh, sorry, I thought it was. I thought that was 2.
There's only 1 sigma. So remember, for multiple bonds, only 1 is a sigma.
Oh,
Exactly
okay.
1. The rest of them are pi. So if we had 4 bonds, what would it be?
Be would that be what, 3 pi and 1 sigma?
Yeah. And why can
Oh,
that
okay.
not happen? And the reason that cannot happen is this is how you get 1 pi bond. And this is how you get another pi bond. So here's a pi and here's a pi. Where are you going to get the 4th? You have to have 2 orbitals that are parallel to one another. And here we have 2 that are parallel this way. And here we have 2 that are parallel coming in and out of the plane of the board. Where else are you going to get 2 that are parallel? And the answer is you can't. That's why we don't have 4 bonds. So again, this is what's happening in bonding here. I don't know if I can do this. Here's 2 p's that overlap, making a pi bond. And these 2 p's coming in and out of the plane of the board, they overlap, making a pi bond. So where are we going to have a 4th p orbital that is perpendicular to all of this? We can't have another one right there where it's slightly tilted, or right there. It just doesn't happen. So that's why you're going to have a limit of 3 bonds in these molecular compounds based on valence bond theory. Now, remember, valence bond theory is not the rule for how molecules behave. It's a model that hopefully predicts how molecules will behave. So it turns out that you can have quadruple bonds, and valence bond theory doesn't work too well for that. Okay? All right. Another thing I'm going to show you is this. So if we draw the Lewis structure, we'd get something like this. You guys okay with that? Now, if we draw this, we could draw it 2 ways. Oh, I do want to go back to this. So this is CH2, CH2. Notice with this pi bond, you have 2 orbitals that are like this. So what happens if you spin the molecule so that the orbitals don't line up anymore? What happens to the pi bond when they're no longer parallel? And the answer is when they're not parallel, they can't overlap. And if they can't overlap, there's no bond. So these things are stuck the way they are, which is kind of flat. So this is not possible. And that's because this p orbital and this p orbital, they don't line up. Are you guys okay with this drawing here? You've got this, and they don't line up, so it's not possible. So on the other hand, this is okay when they're flat. So that means that when we draw this, we want to draw it like this. So I'm hoping this looks like it's flat to you. However, this is also okay. That should look the same as this. One of these molecules is polar and one is not. If you think the one on the left is polar, pick go slower. If you think the one on the right is polar, pick go faster. So how do we pick something that's polar? We look for the most electronegative atom, that's chlorine, on one side of the molecule. And sure enough, this one is polar. This one's nonpolar. Okay, so these are different structures for the same Lewis structure, 3 different molecular structures. Now this one is considered to be the cis structure, and this one is the trans. So how do you get these words cis and trans? If you draw a line through the double bond, if the hydrogens are on the same side, it's cis. And if the hydrogens are on opposite sides of that line, it's called trans. So cis like sisters, and trans like, have you guys ever heard of the Transcontinental Railroad? Transcontinental Railroad? Surely you heard about that in history class. It's a railroad they built from the East Coast to the West Coast. And they met somewhere in, where did they meet? I think they met somewhere in Utah. So they started building it from the West Coast. They started building it from the East Coast, and they met in Utah, right above Salt Lake City. It was a big deal because it connected the East Coast to the West Coast, and you would not have to get on a horse at all to get to one coast to the other, nor would you have to get in a ship and sail through the Panama Canal or around the Horn of Africa. No, it's not the Horn of Africa, the Horn of South America to get to one place to the other. It was a big deal. Transcontinental. Trans meaning going from one side of the US to the other. So here, this is like one side to the other, trans. So you need to know these terms, cis and trans. So I'm going to give you another molecule, and I want you to draw the cis form and the trans form. Draw the cis and draw the trans. When you're done, give me an okay. So both of these are cis, and of course for trans, one hydrogen down, one up. Doesn't matter which one you put up or down. And there you go. So you should know the difference between cis and trans. Which one of these is definitely polar? This one. This one is also slightly polar because the oxygen's over on this side, but it's not very polar. Okay, so that's valence bond theory, kind of in a nutshell. Let's look at molecular orbital theory. So for molecular orbital theory, there are 4 principles. And the way to get to the 4 principles is take a look at this. So AO stands for atomic orbital. So this is a 1s atomic orbital. This is a 1s atomic orbital. And this is an MO, and this is an MO. And this happens to be a sigma 1s star and a sigma 1s MO. So you've got a sigma 1s MO and a sigma star 1s MO. Now, the parts of molecular orbital theory is that the number of molecular orbitals equals the number of atomic orbitals. And when you make molecular orbitals, the best MOs come from atomic orbitals of the same type. So we don't want to do this. We don't want to make MOs out of a 2s and a 1s. You don't want to do that. A 1s and 1s, sure. 1s and a 2s, no. How about a 2s and a 2s? Sure. How about a 2p and a 2p? Sure. Okay. For 2 AOs, you get 2 MOs, one more stable bonding MO, one less stable anti-bonding. How do we designate anti-bonding MOs? With a star. So this is the more stable one. This is the less stable one. And then you use Hund's rule to fill. So if these are 2 hydrogens and we have 1 electron here and 1 electron here, we have to take these 2 electrons and put them into the MOs. So that's what we do. We put them in the lower ones first. So you need to know these 4 principles of MO theory. The number of MOs equal the number of AOs. The best MOs come from AOs of the same type. For 2 AOs, you get 2 MOs, 1 more stable, 1 less stable anti-bonding. And when you put the electrons into the MOs, you put them in using Hund's rule, which basically means you put them in the more stable ones first. And if you have MOs that are of equal energy, you put 1 per orbital before you move on. Let's look at the 2 MO diagrams you need to really know. So this is up to N2. So here's the way I remember it. 3 blind mice, 3 blind mice. See how they run? You got that? Go ahead, you do it. Draw this just like I did and sing to yourself. 3 blind mice, 3 blind mice. See how they run? See if you can draw that. When you can, give me a thumbs up. Practice it a couple of times. Do you know the nursery rhyme I'm talking about, Jackie? 3 blind mice.
I actually haven't heard of that one before.
Really? It's pretty
Yeah.
gruesome later because after 3 blind mice, see how they run? One of them gets their tail chopped off. You got to look it up. 3, see, I'm a little teapot doesn't work. Row, 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 your boat doesn't work. Row, 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 your boat. See, that doesn't work. So you're going to have to Google 3 blind mice and have someone tell you that little story. All right. Now let me show you how to label these. Okay. All of these in the middle are sigmas. And by the way, nitrogen is 1s2, 2s2, and 2p3. Okay. So N2 has 2, 4, 6, 14 electrons. So let's see now. All of these are sigmas. These ones on the sides are pi's. So in all these MO diagrams, the central ones are sigmas. The one on the ends are pi's. Now to label these, you use this 1s, 2s, 2p. So you've got a 1s and a 1s star. So do you remember how for every 2 MOs you get 2, or for 2 AOs you get 2 MOs, 1 bonding, 1 anti-bonding? This is what we do for all the sigmas. 1 bonding, 1 anti-bonding, 1 bonding, 1 anti-bonding. These 2 are 1s's. The next 2 are 2s's. The next 2 are 2p's. And here you get these are 2p's. And remember, the lower one is bonding, the upper one is anti-bonding. So this is one of the MOs you should look at, or you should understand. And here, if we have to put 14 electrons in here, let's put them in there. 1, 2, 3, 4, 5, 6, 7, 8. Here's where it gets tricky. 9, 10, 11, 12, 13, 14. And that's N2. Here's what we can get out of this MO diagram. N2 is diamagnetic. No lone electrons. They're all paired. We can get N2 has a sigma bond. N2 has 2 pi bonds. So let me show you how you get a sigma bond out of this and 2 pi bonds, okay? Are you ready for that explanation? Okay. So if you have 2 electrons in a bonding orbital, that counts as a bond. So do you see this here? This is a single bond. 2 electrons in an anti-bonding orbital cancel 2 electrons in a bonding orbital. So do you see these 2 electrons? They cancel these 2. So no bond. Are there any others here that cancel? And the answer is these 2. These 2 cancel these 2. So there's no bond. Now, do you see these 2 electrons in a sigma 2p orbital? That's a bond. Do you see above? There's no electrons, so these guys don't get canceled. So there's 1 sigma bond. You see these 2 here? They make a pi bond. Do we see 2 electrons in the star above that cancel it? The answer is no. So therefore, you get a pi bond here, and you also get a pi bond there. So the 2 pi bonds. So do you understand how to get the number of bonds? So here we would say that the bond order is equal to 3. Are we good on that? If we're good on that, give me a thumbs up. Okay, cool. And we also can write the electron configuration. Now these guys here are considered to be core electrons, and these guys are the valence. So here's how you write the electron configuration. We're not going to write these guys out, but we write them after that. So here we got sigma 2s, 2 sigma star 2s 2. Notice that the MO goes inside of parentheses and the number of electrons is on the outside of the parentheses. So I've just drawn these 2. What do I do for the 2 P's? I do that. I combine these together because they're the same energy. And then we have a sigma 2s 2. And that's the electron configuration. Okay, now I said you would need to know 2 MO diagrams. Let me show you the other one. So this is the MO diagram for O2, F2, and E2. So do you see how this is a little bit different? Instead of a triangle and a triangle, we've got a triangle, then an upside down triangle. The other one looked like this. And you see how it switches and flips on the second one? Okay, so I'm going to ask a question. Whoever gives me the thumbs up first gets to answer it. What type of orbitals are these on the outside? Are they sigmas or pi's? Okay, Harry, what are they?
Are they pies?
They are pi's. Okay, Jackie, these are pi's. Which one is a pi star?
Um,
The one on top.
okay.
That's simple. So the outsides are pi's, the one on top is a star. Okay, Jackie, I'm going to give you a chance to redeem yourself. What kind of orbitals are these up the middle?
Would those be,
Not pi's, but
oh, sigma.
sigma.
orbital.
Okay, let's look at these two on the bottom. Which one is the star?
The top one?
How about the next two? Which one's the star?
The top one.
How about the next two? Which one's the star?
The one at the very top.
There you go. Now, these guys are all 2p's. And you'll notice we have 1, 2, 3, 4, 5, 6 2p's. And the reason for that is that each oxygen has 3 2p's. So when you make MOs out of them, you get 6 2p's. What are these guys at the bottom? They're 1s's, and these guys are 2s's. So O2 has 16 electrons total because the atomic number on oxygen is 8. So what I want you to do is I want you to put the electrons into this guy, and I want you to comment on the magnetism. I want the net pi bonds. I want the net sigma bonds. I want the bond order, and I want the electron configuration. So put those electrons in here, and there's 16 total because we're talking about 2 oxygens. Well, I'm going to pause this. Harry, you're going to remind me to resume recording, right? So with 16 electrons, because oxygen has 8 valence electrons, I put them in like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So magnetism, paramagnetic. Why? Because we have lone pairs. Excuse me, not lone pairs, lone electrons. Net number of pi bonds. These two cancel, these two cancel. This does not cancel, so we've got a net of 1 sigma bond. Here, half of this cancels, so this would be a bond that cancels with half of it, so that's half of a pi bond. Here, this would be a bond, but half of it cancels. So that's a half of a pi bond. What's a half of a pi bond and a half of a pi bond? 1 pi bond total. Bond order is 2, 1 plus 1. Electron configuration is the core electrons, 2s2, sigma 2s2. That's a really sad looking sigma. Sigma star 2s2, sigma 2p 2, pi 2p 4, and then pi star 2p 2. Now, another way to get the net number of pi bonds is this way. The net is going to equal 1/2 of the bonding electrons minus the anti-bonding electrons. So if we take a look at this configuration over here, how many bonding electrons do we have that are pi? Well, we don't look at these. We've got 1, 2, 3, 4. 4 bonding electrons in the pi, and we've got 2 in the anti-bonding. So you get 1. So do you understand what BE stands for? Bonding electrons. And these are the anti-bonding. So you can do that for the net, or you can do it for the total. You can just say, hey, I want to know the bond order total. You look at all the bonding electrons, all of the anti-bonding electrons, subtract them and take half, and you got the number of bonds. All righty. So that's MO. Now, I want to give you one little brief thing. Is sometimes you only do the valence electrons. So for O2, we're looking at 6 plus 6 for 12 valence electrons. Now, if we're only doing the valence electrons, we only do the valence orbitals. So for O2, it would look like this. So this is pi, 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 sigma, 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 star, 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 star. And the 6 at the top are 2 P's. And these are 2 S's because the 1 S's are not shown. We don't show the core electrons. So when we put the 12 electrons in here, we get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And here, the magnetism is still para. The net pi is 1. The net sigma is 1. And the electron configuration is still core. And then what you see here. So I'm telling you this because sometimes the book only shows you the core, the valence electrons, and they don't show you the core. So when you're only looking at the valence molecular orbitals, you're only going to look at valence electrons in those molecular orbitals. So try not to be confused by that, okay? So just a little bit of warning. Sometimes they don't show the core. But we all know that you need to work out your core. Otherwise, you're going to get a bad back. All right, that's it, people. We'll see you Wednesday.
Yep. All right, well, bye, guys.
Bye.
See you guys Wednesday.
Have a good day.
You too.
Yeah.